This video demonstrates how you can use a tool like MATLAB to find prediction models with Karima models. So the previous video showed how you could form a prediction based on a Karima model, but the presentation we gave was solely algebraic. In this video we're going to give some numerical examples just so that students get an idea of how to do this in practice. Now I would recommend that you use tools like MATLAB or similar tools to do the number crunching, because really prediction is not a paper and pen exercise. But what you will notice is the code requirements using the method proposed here are essentially trivial. They really are. You could write them in 5 or 10 minutes, and most critically they are much easier than any code you would have to write using things like Diophantine methods. The previous video then developed the following results. We said if you had an incremental model, something like this, capital AY equals B delta U, where capital A was the original denominator times delta, then you could show that a vector of predictions, y future, k plus 1, could be given by expressions of this form. So you'll see we've got CA inverse CB times delta U future, CA inverse HB times delta U past, and CA inverse times HA times Y past. Now you obviously can put more compact expressions here. You can write capital H for CA inverse CB, capital P for CA inverse HB, and capital Q for CA inverse HA. And so what we're going to do in this video is we're going to focus on how you get H, P and Q, which are the key matrices you need for predictive control. First example then. We're going to take an A here, 1 minus 0.8 Z inverse, and a B, giving us 2 Z inverse plus Z minus 2. Very simple system so that you can see the numbers and you can see what's going on. If you calculate capital A, which has given us A delta, and you may remember delta is 1 minus Z inverse. If you multiply that out, you see this is capital A, 1 minus 1.8 Z inverse plus 0.8 Z minus 2. Now, I'm going to take a horizon of 4 to keep things simple, so you can keep it on a single page. So the definition of CA, you'll notice you simply write out the parameters of a capital A matrix, and you can put them, if you like, in columns. Can you see there are the parameters of the A matrix, 1, minus 1.8, 0.8, and you'll see that's precisely the parameters given up here. You can do the same on the second column, the same on the third column, the same on the fourth column, but the key thing is CA is square. Alright, so if we write that, it's square, so when you run out of space you no longer have to write the coefficients that are missing. And you'll see it's lower triangular, so all the top part of the matrix are zeros. Similarly, if we look at CB, we're just going to use the parameters of the B polynomial, which are here, 2 and 1. So you can see vertically, I simply entered the parameters, and then when I start running out of space, I just put the parameters that will fit. So hopefully that's straightforward. The best way to do this is entirely up to you, but hopefully it's obvious that you could produce a piece of code to do this very easily, probably filling in the diagonal, then the subdiagonal, and the sub-subdiagonal, and so on. What about the HA matrices? Well, what you'll remember with HA matrices, what you're doing is you're not putting the entire number of coefficients from the polynomial. You basically ignore the first one and see what's left. So you can see I've got minus 1.8 and 0.8 in the first column, and then you've got one fewer in the next column, so I've just got 0.8, and then it goes to 0. HB, similarly, you don't use the first coefficient, you start with the second coefficient, so I've just got 1, and there's only one column, because after that I'll have nothing left. Hopefully you can see very easy to generate these matrices, and if you needed to do it with code, that would be equally trivial. Now the definition of H, CA inverse CB, I can just write that down by inspection with any decent software, and similarly for the definition of P and Q. And we'll show this in MATLAB in a few slides' time. Now some comments. You will notice, however, that doing the matrix multiplication is not a paper and pen exercise. You could do it for horizons of 2 or 3 or 4, but certainly not for horizons of 7, 8, 9, 10, 20. It would be too tedious. So you need to create some code to do this. Now, as the turplets matrix CA is lower diagonal, and you'll see it's striped, it's well conditioned for inversion. And so if you wanted to, you could do some specific code to do the inversion of this, which was very, very fast. But the key thing is it's well conditioned, so you don't need to worry about whether the inversion will give you problems. Similarly, if you are really bothered about computational load, which I doubt you are in a modern world, it's clear that many of the implied multiplications to find H, P and Q are actually common, they're the same, and thus you can do this very efficiently if you need to. But for most users, what you're interested in is transparency of the code and what's going on and getting the right answer, less so in the computational load, because the computational load of matrix multiplications is not a big issue in the modern world. So some observations. You can show, and I suggest you prove this if you don't believe it, that CA inverse is actually equal to the C matrix of 1 over A. I can use a simple example to show this that you can basically do on code yourself. If you wrote A equals 1 minus 0.8 Z inverse, and then you said, right, I'm going to find 1 over A, you'd find you got this 1 plus 0.8 Z inverse plus 0.8 squared Z minus 2, and so on. Now, if you form the CA matrix, that should be lowercase a in this particular case, apologize. If you were to do that, you would find you get this matrix here, and if you stick that into a piece of code and do the inverse, you'll get this matrix here, which clearly is the turplets matrix based upon this polynomial here. However, it's easy to do a generic proof, so I will leave that to you. Okay, on to the numerical examples. What we're going to do now is we're going to switch to MATLAB and we're going to demonstrate how simple the code is for forming the prediction matrices. And we're also going to include a multivariable example at the bottom to show that the code for the multivariable example is in fact identical. And that's really nice because it keeps life simple. So we go to our MATLAB window, we find our file. Okay, so first thing, let's enter our A polynomial. There it is, 1 minus 0.8. Enter a B polynomial. There it is, 2, 1. And then we basically multiply this A by delta to get your capital A. So you can see you can use the conv function in MATLAB. And now I've written this piece of code called CAHA, which if you look at it, you'll see it's very, very short, to find the CAHA matrices. So if I write that, and there you can see, there's the CA matrix with the stripes, there's the HA matrix. Very easy, just define them with a simple command like that. Similarly, I can do CB and HB, and then I can get CA inverse. There it is. Okay, so there's my CA inverse if you needed it. You can see I've just used the inv function on MATLAB because it's simple, and then I just write down H equals CA inverse times CB, P equals CA inverse times HB, Q is CA inverse times HA. So you'll see the coding requirements to get the prediction equations are really very, very simple and very, very transparent. And the only code I had to write was this CAHA program to produce the striped matrices, and that program really is very, very brief and very simple to write because the matrices are striped. If I wanted a slightly more complex problem, let's say the horizon is now going to go to 8. You'll see I've got an 8 here, so I can generate those matrices, and just if you don't believe me, let's do, oops, typed in the wrong place there. Here we go, CA, so you can see there it is, it's 8 by 8, it's got the same stripe nature, so I can do that. I've deleted a bit of my code by accident there, haven't I? We'll go back later. There's my CB, and again, you see I can do my CA inverse, and I can do all the other commands exactly the same, no difference because of the horizon. I've got exactly the same pieces of code. Okay, so it's horizon independent. The code is the same. I can change the horizon. It doesn't change the code. It doesn't change anything. What if I had a higher order system? So here I've got an A, which is a bit bigger, You can see it's a lot longer. A B, which is a bit bigger, but you'll see exactly the same command. I first multiply the A by 1 minus delta to get capital A, exactly the same code as before. I find the CA, HA matrices exactly the same as before. Here I've used a horizon of 10. Let's just have a look and see what that is. And there you can see, alright, it's filled the screen, you really don't want to display it, but you'll see clearly it's got this striped nature. Very, very easy to define. I can do the CBHB, there we go, and as before, exactly the same lines of code. So you'll see, just because A changes, just because B changes, just because the horizon changes, the code is still fundamentally trivial. Now I could do a multivariable system. The problem with multivariable systems is in fact defining the A and B to start with. So what I'm going to do is put those in quickly for you, and then I'll do capital A so you can see. So the way this works, this is a 3 by 3 system. So you'll find you have a block here which goes with z to the naught, and then you have a block here. Is that 3 by 3? Yeah. Oh, sorry, I've not read the numbers carefully. There we go. So there's the first block, there's the second block, and you'll see there's 4 blocks altogether. But so basically, as long as you arrange your matrices in blocks, this one goes with z to the naught, this one goes with z to the minus 1, this block goes with z to the minus 2, and so on, then you can define them in a straightforward fashion. Now I need to get rid of these, because otherwise they're going to get in my way when we do the next bit. Right, so next I calculate an equivalent of the delta operator. There it is, and I multiply my A by the delta operator. But again, you see conceptually exactly the same steps. The algebra is a bit more tricky because you're dealing with matrices, but conceptually it looks the same. But you'll see exactly the same program, CAHA. So once I've defined my A and my B as matrix polynomials, the remaining steps are no different from what I had in the CISO case. Okay, the 3 here in the CAHA tells the program this is dimension 3, so all the blocks come as 3 by 3s. And then here, you'll see I can do my CAHA. If I want to see how big they are, to see what's going on, there you can see H 30 by 30. Its blocks are 3 by 3, and the horizon is 10. The P 30 by 3, the Q 30 by 12. And hopefully you're convinced the MATLAB code is easy. So in summary, it's common to use discrete models for predictions, and in this video we've shown how Karima models can be used to form n-step ahead predictions, and in particular it's shown that software development for these prediction matrices is trivial, and it's literally just a few lines. Okay? Personally, I would recommend avoiding Diophantine approaches to prediction with a transfer function case, because these are somewhat obscure and cumbersome, and they're not really any more efficient either.